Hello and welcome to C++ Weekly. I'm your host, Jason Turner, available for code reviews and on-site training. This episode, I want to indirectly, or directly, I guess, address the previous episode that I released on how, in the most extreme cases, I could demonstrate that my very simple implementation of a pair struct could be 310 times faster than your standard library's standard pair. Now, I don't want you to take away from this the idea that you can't trust your standard library. So in this episode, I am going to give you 3 steps for how to restore trust in your standard library. Now, the very first thing that we need to do if we want to trust our standard library is just simply know what your library does. This might sound obvious, but actually, let's just open this up as a nice comment block here. Funny notepad that I have here that needs comments around my my text. All right, if you've been watching this show for more than 2 weeks, you've probably seen CPP reference here. And this gives us a great overview of what our standard library does. But there's a couple of things that might not be incredibly obvious and a few places where we need to dig in from time to time. Now, I complained recently about the 13 confusing constructors for basic string. So let's go ahead and click in here, and you can see that in the list of all the functions, the constructors are not listed out separately, so we don't see all of those. So we actually have to go and then click on constructor to see all of these different constructors that actually exist. But once you get in here, you can start to recognize some things. Like, for example, yes, there are a lot of constructors, but we can see that in C++20, we got constexpr constructors. So that gives us a clue that it is actually possible to use this type in a constexpr context. And that is an important thing to know when we're going to use something in the standard library, particularly if you're concerned about pre-calculating any resources at compile time so that you don't have to do those things at runtime. Knowing which things can be used in a constexpr context is a very important thing to know. If we were to have started by going and looking and seeing what are the constructors to pair, then we would have immediately noticed that pair does in fact have constructors. And by having constructors, we might have the question of, well, how efficiently is that data passed into the underlying data structure? And it's not necessarily something that we stop and think about all the time in our standard library, or when we're using any library, or even writing our own libraries, actually. But it is something that we should occasionally stop and consider. This is no worse in most cases and in most ways than anything that you would have created on your own, because most people don't think about creating a struct with only public members and no constructors so that you can directly initialize the data. But we can also come down here and see that there is some reason for this complexity because it does have this piecewise construct thing, which I don't believe we've ever covered on this channel, but it does have some interesting use cases. So when we see something like that, and we might immediately go and say, well, how does its closely related friend tuple compare? So we can click on tuple and we can dig into its constructors. And we are able to see that constexpr is not actually explicitly listed here, which is unfortunate. It looks like we need to do an update on CBP reference, but it does say constexpr since C++14, so we know it is constexpr. We know that it has a perfectly forwarding constructor, and we know that it does have some implicit, potentially implicit conversions from pair to tuple, and I don't really like implicit conversions, but we can go here and we can see, oh, we know that it can be implicitly converted from a pair to a tuple. that those conversion operations exist, and that is something that we should perhaps be aware of. Now, there's nowhere, as far as I know of, to find a list of all of the implicit conversions inside the standard library, but there are a fair number of them, and one of them that annoys me the most often is the constructor for optional, because people just assume, oh, an optional is a relatively cheap thing to use, but they never stop and consider that if you pass a value into something expecting an optional, it's actually going to have to do a copy or move. It can't directly initialize those data members either, and you are going to pay some level of cost here. And we can see templated constructor right here. So this is a conditionally explicit templated constructor from any value into the optional. So let's see, what is it conditionally explicit on? The constructor is explicit if and only if is convertible between these two types is false. So it does a type trait check here to see if they're false. So these are the kinds of things that we start to notice as we dig into our standard library. Now, the next one is kind of a big one for me. Sometimes we need to know, and it can actually be very important for our performance in our system, if a function or constructor might implicitly allocate to do some operation behind the scenes for us. This is not definitely always obvious. So we were just looking at tuple and pair. Those are never going to allocate. And we do know that because we always know at compile time the size of the things that are contained in them. So this is also true for variant. Variant is never going to allocate. The object representation of t is allocated directly within the object representation of the variant itself. So variant is not allowed to allocate additional dynamic memory. This is something that we can look up. But there are a few types in the standard that might allocate and might not allocate, and we don't necessarily are aware of those. So standard any is one of them. Implementations are encouraged to avoid dynamic allocations for small objects. So standard any, it's going to do a small object optimization just like standard string does. So standard function doesn't have the same wording in it that any does, but I know from experience and from looking that there is also a small function optimization for standard function. Now, you might not be aware at all that standard function might need to allocate, but there are actually some functions that are bigger than other functions. And if you stop and think about a lambda with a lot of captures, that is going to be much bigger than a lambda with no captures, which is the size of just simply a function pointer. So that was any in standard function. And now we've played many times on this show with standard string and its small string optimization. So for things that may or may not allocate, most of our standard containers, etc. Now, node-based containers such as set and map and list are actually required by the standard to make an allocation per node. And that's not necessarily immediately obvious as well. But if we look at map, something that we've never covered on this show before either, as long as we're on the topic of things that haven't been covered before, is this extract. Extract and merge. This is where we can extract nodes from the container and splice them into a different map or a different set or something like that, which this is only possible if the nodes were individually allocated. So this is one reason why these containers are not ideal for many situations. So things that might allocate: string, function, and any. And if you're careful with all three of these, you can actually use them in a scenario where they would never allocate, but it's kind of difficult to know how large that small buffer is that is available to you, and it's going to take some experimentation depending on the platform that you have. And then it's important to know the things that will never allocate: pair, pair-like things, tuple. variant, and array, which we haven't brought up yet. And this is another fascinating look into our standard library. If we pull up array, notice that there is no link for constructor. Now, everything that I mentioned in that episode about standard pair and digging into what its constructor may or may not do and whether or not it would be inlined is all completely irrelevant when we talk about standard array. Not only will it never allocate, it doesn't even have a constructor. So if we directly initialize our standard array, we will always get the most efficient operation possible. Now, generally speaking, our algorithms are never going to allocate, but there are a couple that are allowed to allocate to meet efficiency requirements, and therefore I believe are still not context-per. So it comes down to the stable sort algorithms. We've got stable partition and stable sort. And if we click on these, note, this function attempts to allocate a temporary buffer equal in size to the sequence to be sorted. If the allocation fails, the less efficient algorithm is chosen. So this is an algorithm that is allowed to allocate, and you'll note that it was not made context-per in C++20. So the various stable sort, stable partition, that kind of thing, they might allocate. Now, if an algorithm is context-per enabled, as of C++20, it will never allocate. So you know that you can safely use this in a constrained environment. Okay, so that's the main thing. You need to take time to understand what your standard library does. And you can take time to dig into just a few of these things and learn. Here's another great example. Standard optional will never allocate on its own. If the object contains a value and type T is not trivially destructible, then it destroys the containing object. Note, if T is trivially destructible, then this destructor is also trivial, so an optional of T is also trivially destructible. This is actually super important from a performance standpoint. So these kinds of things were taken into account for you by the standard library and by the standard library implementers, and getting them right on your own is actually fairly surprisingly difficult before C++20. So this is not a conclusive list of these things, but it's things to be aware of. Okay, so we've taken time to learn what our standard library does. Step 2 in trusting our standard library is to know that our libraries are very well tested. Now, if you consider that the standard libraries are used by literally millions of programmers all over the world, and this is independent of whether you are using libstd++, libc++, or Visual Studio standard library. So effectively, and at the moment, I don't remember if MSVCs has its own name. They're very well tested, each of them used by millions of programmers all over the world. If there's a bug in the standard library implementation, it is going to be found and fixed pretty quickly. And they're all open source. For some of you, it might be surprising to learn that Visual Studio's standard library is actually open source as well, but not only is it open source, it is actually accepting actively contributions from the community. So I just jumped down here into GCC, a mirror of GCC's standard library implementation here, libstd C++, version 3, its test suite. Its test suite is huge. And for any of these things, we can click on them and we can say, okay, strings, let's look and see what string tests there are. And there's so many tests, and some of them are even labeled based on like specific bugs that they were found with or whatever. And oh my goodness, you know, we can get down in here and even like 5 levels deep, there's a half dozen tests. And for bonus points, actually, if you pay attention here, you'll actually see that like Visual Studio will run libc++'s test suite to make sure that they're implementing the same things in the same way. So not only are they all very well tested, they've got just a crazy amount of interpollination, if you will, between the implementations and the test suites to make sure that they implement the same things in the same ways. And you can go in and dig in any of these things if you want to. Now, taking it to the next level, I have this archived mirror link of libc++ up, but that's not really the point. This was just one of the fastest ways that I could find this code. If you go down into fuzzing, you can actually see the fuzz testing harness that exists for libc++'s implementation. And you can see that all of the standard algorithms, or many of the standard algorithms, are actually being continuously fuzz tested. And if you don't know what fuzz testing is, you got to check out my other videos about that, because this is incredibly important to making sure that there aren't other bugs lurking in the standard library. So fuzz testing even is occurring for our standard algorithms here. Now, hopefully that convinced you, at least at a high level, that the standard library implementations are very well tested, and it's virtually impossible that your library that you've written internally for your organization is as well tested as your standard library implementation, because you don't have millions of users all around the world that rely critically on your containers and your algorithms that you're providing inside your organization. Okay, they're all very well tested and they are open source. Now, on the topic of open source, and this is the third and final point, you can go and read the source code. And I'm going to jump into one very specific case where I think this matters. But you can actually dig in and you can see how and why something was implemented in what specific way and time and why, and see the history of it, since they're all open source, and we can get into some of their history here. Now, one of my friends pointed this out to me several years ago, that no matter what they did, they were getting some weird like loop unrolling behavior in GCC's standard library. And they had to dig in to the source code and look at GCC's standard algorithm implementation to figure out what was going on. So I have libstd++ up here, and in case you forgot, this is the standard library implementation from GCC. Now I believe this is the current version of this file, but I could be wrong. This was the one that I found with a Google search. It is therefore also likely to be the one that you would find with a Google search. Now I could jump in on my console, but then that would mean my screen would go from white to black, and those of you who are watching in a dark environment or something would complain that I had just blinded you with a quick changing brightness level of the screen here. So I'm not going to do that, but we're going to browse down through this version. And this is just the implementation of find if. So I've got this find if, overload used to find algorithms in the input iterator case. This is an overload used to find algorithms for the RAI case. This is the random access iterator. So now this is another thing that our standard library implementations are doing that you probably aren't doing, and that is many of the algorithms are actually optimized specific to the type of iterator that was passed in. So a random access iterator, like one from a vector or from standard string, can have certain optimizations applied to it that a forward iterator, input iterator from standard list cannot, because find if does this linear search. So this version that requires a random access iterator from the GCC standard library implementation actually has baked into it a partial loop unrolling. It looks to see how many elements is it going to need to search over, and then does a divide by 2 here, and then gets an idea, or sorry, not a divide by 2, that's a right shift by 2, that's a divide by 4. gets an idea for how many trips it's going to make through this code with this divide by 4, and then you can see it's done a partial loop unrolling of going bang, 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 4 at a time, incrementing the iterator, then jumping back up to the top. Now, my understanding of current compiler technology is that this is a completely outdated optimization here. You should just be relying on your compiler to know how many elements are going to be looped over and do this partial loop unrolling. And I was just digging into this. I'll bring it up. This is GCC's list of options that control optimization. Move loop invariants, align loops, finite loops, rerun CSE after loop, loop interchange, loop unroll and jam, peel loops, split loops, tree loop distribution, tree loop vectorize, unswitch loops, version loops for strides. You know, have fun, dig into these things, go and look at all the kinds of optimizations that GCC can do for loops. It is absolutely insane. So I think we would probably be better off if we didn't have this code here. And this is the kind of thing that in some situations is actually going to make debugging our code a little bit harder, because we're going to go 4 levels down into our standard library and end up in underscore underscore find underscore if while we're debugging and see this partially unrolled loop that's going to be a little bit more difficult for our brains to process. But if this gets in your way and this is a problem for you, you can actually go and you can see this. You can read the source code and you can implement your own find if you really, really need to, but it's almost certainly not what you need to do. So got a little bit more heavily weighted towards item number 1, this know what your library does, but you need to get familiar with the types, with the algorithms, what they may or may not do. There's not so much here that you can't keep it all in your head, and you can quickly go back and look at CPP reference if you need to. You can know that your standard libraries are very well tested, probably the most well tested C++ code that exists. I would say that's probably almost certainly true. And you can go and you can read the source code. If something's getting in your way, you can figure out why. And in those very rare cases where you need something different that the standard library can't provide for you, then you can go and implement your own thing. But just be aware, it's not going to be as well tested as the standard library version. So I hope you liked this episode of C++ Weekly. I think you should subscribe, give it a thumbs up, leave comments below.